All right, if you watched those last two derivation videos, so we came up with 4 different equations for the Doppler effect, you might think, oh, this is really difficult and I don't know when to use what and I don't know how to do this. This video is supposed to bring it all together to make it all nice and easy for you, and we're going to do all your problems in your book for them to get checked off also. So just to review, we have some symbols. We want to make sure we know what they are. So we have frequency, which is just by F. That is the actual frequency of like whatever the sound is. We have F prime, which is the effective frequency, basically the frequency that the observer is going to be hearing during the situation. So there's the actual frequency and the frequency that the observer would actually hear. There's also V, which is the speed of sound. There is Vs, which is the speed of the sound source. If the source is moving, it would be Vs. This Vs is not the speed of sound, it's the speed of the sound source. And then we have Vo. If the observer happens to be moving, then that's how fast that person is moving. So in these top 2 up here, these are the first 2 we derived in my first video. We have an observer who is stationary. The observer is not moving at all. So you'll notice that there is no VO. There is no VO in either of these equations, right? But the sound source is here. The sound source is moving toward, right? The sound source is moving toward, and here the sound source is moving away. Okay, so there is a Vs in both of these. Now both of them have the speed of sound, which is V, but there is a Vs in here. You'll see that if the sound source is moving towards a stationary observer, then it's a minus sign down here in the bottom. But if it's moving away from a stationary observer, it's a plus sign down here in the bottom. So those are the 2 equations if something's moving towards you or away from you, the thing that you're normally experiencing. Like if a race car went by you really fast, you'd hear a really high frequency here, and then it dropped down to a low frequency here. Okay, the other situation is you could be moving towards a sound source that's not moving. So in these 2 equations, you'll notice there's a VO. That's the velocity of u. You're running towards it or running away from it, but there is no Vs in here because the sound source is not actually moving. So if your observer is moving towards, if you're moving towards a stationary sound source, okay, you're moving towards it, you would hear a higher frequency, right? You'd hear a high frequency, and you'll notice there it's a plus sign right there. Okay, now up here, sound source moving towards a stationary observer. This was also a high frequency, but down here in the bottom, see, it was a minus, right? Okay, so up here, sound source moving away from a stationary service, it was a stationary observer. It was a low frequency, and it was a plus sign. But here, down here, an observer moving away from a stationary sound source, it would also be a low frequency. But up here in the numerator, you have a minus sign. So, it'd be a nightmare. What happens if, there's like a cat making an annoying sound and it's like running towards me, okay? And I get annoyed with it, so I run towards it, right? So now I'm running towards it and it's running towards me. What kind of frequency would I hear? How would I solve that kind of problem? So the way we solve that problem is we combine it into, combine all 4 of these equations into one Doppler effect equation. One Doppler affected equation, and then we got to look at our pluses and minuses to know what's happening. So the way that this would look, I could combine all these. They all start with this, right? The effective frequency that I'm trying to figure out, and then that would equal the actual frequency of the sound, whatever the actual frequency of the sound source is, times, and then there's this ratio here. Now in the numerator, down here, let's look at down here, we have a numerator here. I have V plus VO or I have V minus VO. So I'm going to write in the numerator V, I'm going to do plus minus VO. I'm going to do it this way, okay? over, and then what do I have in the denominator for these? I have a V minus Vs, or I have a V plus Vs. So I'm going to do a V minus or plus Vs. Okay, now I did this on purpose this way. It's how I want you to it's how I have the equation written down in your sheet. It's a plus, and then a minus, and then a minus, and then a plus. So keep it that way. Keep the pluses on the outside and the minuses on the inside. Plus, minus, minus, plus. Plus, minus, minus, plus. And if you do it that way, then you can remember this. Towards, away, towards, away, towards, away. Okay? Towards, away, towards, away. So if you have a observer moving towards the sound source, you'd use a plus. If the observer is running away from the sound source, you'd use a minus. If the sound source is running towards you, the observer, then you use a minus. If the sound source is running away from you, you'd use a plus. What if I have a situation where here's a cop car, and I see him, and I am running away from him for whatever reason, and he's coming towards me. Okay, what kind of a frequency would I hear? Well, I do the speed of sound, right? Speed of sound, and then this is the observer. That's me. Am I running towards or away from the policeman? I am the observer. I am running away from the policeman, so I'm going to use the speed of sound minus how fast I'm running. Okay? Now what I do in the bottom. Here's the speed of sound, and this is the sound source. This is the cop. So is it the speed of sound minus the speed of the policeman, or is it the speed of sound plus the speed of the policeman? Well, what is the policeman doing? He's coming towards me, right? He's coming towards me. So I would use a minus here on the top. Okay? I'd use a minus on the bottom because I'm going away from the policeman, but he's also coming towards me, so I'd use a minus on the bottom as well. I could put all those velocities in, and I could get the original frequency, and I could solve for the effective new frequency. Okay, so all we need here is this equation right here. This is what the equation is written on your sheet, and you can remember it, and you just got to remember the pluses go on the outside, the minuses go on the in, and it's towards away, towards away. Okay, that's how you're going to use this thing. So we have 4 problems in your book on page 82 that we're going to go through and do and solve right now. So the first problem, I have the equation written over here on the right side every time. So in this first problem, 714, we have a car traveling 20 meters per second towards you, is making a sound of 220 hertz. Let's take an inventory of the problem here. We have a car traveling 20 meters per second. That car is making the sound. So that is the velocity of the sound source is 20 meters per second. Okay. It's making a sound of 220 hertz. So that's the frequency, the actual frequency, 220 hertz. If the temperature is 25 degrees Celsius, what pitch? Okay, so why did they give us 25 degrees? Well, we can figure out the velocity at speed of sound with the temperature. So that's what we're going to do. We're going to do the velocity would equal 331.5 plus 0.6 times 25. That's how you, if you remember, that's how you figure out the velocity of the sound. That was 346.5 meters per second. So that is V, okay? The question says, what pitch do you hear? So what is the effective frequency? What's F prime? That's what we're trying to figure out. What whole, and there's another question. What whole number drop in frequency would you hear as it passed? Okay, so this is actually a 2-part problem. Okay, 2-part problem. We want to figure out what frequency would you hear if it's coming towards you, and then what frequency would you hear if it's going away from you? Okay, so how fast am I going? I am going 0, right? I'm going 0. So this top part of the equation, right here, I put 0 in for the velocity of the observer, and this whole top part of the equation actually then is just a V, right? It's just a V. Okay, So if I want to figure out coming towards me, right, I would do f prime equals the frequency, which was 220, times the speed of sound, which is 346.5, over the speed of sound, 346.5. And now do I use minus or plus? Minus or plus? Well, the car was traveling towards me at the beginning, right? Towards me. So I have towards, away, towards, away. So I'm going to do a minus for the first one, right? And that's the velocity of the source is 20. So I'm going to figure out something here. I haven't actually done that. I'm going to let you do that. You'd figure out some frequency here. It should be higher than 220 because it's coming towards me. Now I can figure out what's the frequency I'd hear if it's going away from me. So that would be exactly the same as this, 346.5 over 346.5. But this time it'd be a plus, right? Towards, away, towards, right? This is towards, away, towards was minus, and now away. If the sound source is going away from me, it's going to be a plus, okay? Plus 20, and I'd get some frequency there. Now, this should be lower than 220 because it's going away from me. So I wanted to figure out what is the whole number drop in frequency. So all I have to do is subtract those, and I would get a drop in frequency. I have calculated that out, so I'll give you an answer, 234 hertz, and see if you get the same thing for that. So in that kind of problem, you actually had to do twice. Sorry about that. You have to do the frequency as it's approaching and the frequency as it's departing, and then you'd have to subtract those to see what frequency drop you would have had for that. Okay, next question. 7.15. We have a cat is running away from you at 12 meters per second. Okay, so let's take an inventory again here. We have a cat. The cat is making the sound source. So that's the velocity of the source is 12 meters per second. Making a sound at 300 hertz. That's the frequency. 300 hertz is the sound that it's making. If you are chasing the cat at 40 meters per second, so you're the observer listening to the cat, but you're actually moving. So we have a velocity of the observer, that's 40 meters per second. And it's a 15-degree day. Okay, that's how we figure out our speed of sound. So I'm going to do 331.5 plus 0.6 times 15. And that gave me a velocity, I did calculate that out, 340.5 meters per second. There's the velocity, okay? What would be the frequency of the pitch you would hear if this was the situation? Okay, so see, we have a cat running away from us, right? A cat running away from us, that's the sound source. So down here in the bottom, right here, we're going to put in 12 for this VS. And we're going to put in 340.5 for the actual velocity of sound. But are we going to use a minus or a plus? Well, what's the cat doing? It's running away. Towards, away, towards, away. Okay, so we're going to use a plus on the bottom here. All right, what are we going to use on the top? Up here we have the velocity of the observer. That's me. I'm moving at 40 meters per second, so I'm going to put 40 in for the VO. And the speed of sound is still 340.5. But am I going to use the plus or the minus? Towards, away. I'm going towards, right? Towards the cat. So I'm going to also use a plus on the top here, right? Okay. Cat is running away from you at 12 meters per second and is making a sound, and you are chasing the cat. So I'm actually using a plus on both sides. So how do I do it? New frequency, frequency prime equals the old frequency, the actual frequency, I guess I should say, 300 times. And then what do I have here? I have 340.5 plus the velocity of the observer is 40 over 340.5 plus the velocity of the sound source is 12. Okay. Now, am I expecting a frequency? Look at common sense. Am I expecting a frequency greater or less than 300? Well, how is this fraction going to come out? It's going to actually be greater than 1, right? Because I'm catching the cat. Eventually, I'm going to catch the cat. So I'm going to hear a frequency that's higher than the 300. Okay, so you can figure all this out. Try your math, and if you get it right, I think it's 324 hertz. If I calculate it right, that should be the frequency that I would hear, which makes sense because it is higher than the 300. Okay, if you know how to do all these problems, you're going to have no problem on the Jedi trial or the ELAB. Last problem is an exciting problem. I came up with this a couple years ago. I think it's kind of cool. It gives you very little information, which makes most students shut down. But you, of course, know not to do that because it's exciting. It says an object passes you on a day where the temperature is negative 2.5 degrees Celsius. Okay, so we can real quickly here figure out the velocity, speed of sound. It's going to be 331.5 plus a minus, or you could just do a minus 0.6 times the 2.5 would give me a velocity of 330 meters per second is how fast the speed of sound is going. Okay, so we'll use that, but we won't use that to the very end, actually. So an object passes you on the day where that's the temperature, that's the speed of sound. How fast is the object moving if you would hear an octave drop in frequency? An octave drop in frequency. Okay, so this is pretty awesome. We could have a, what would be so that means the frequency you hear as it's coming towards you, right, is how much bigger than the frequency you hear when it goes away from you? Well, it's an octave drop. So how does an octave work? You double a frequency, right? So the frequency I hear coming towards me would actually be twice as much as the frequency I would hear going away from me, right? Okay, how do I figure out the frequency when it's coming towards me? Well, that would be equal to f times on the top the observer is the observer in this whole problem is not moving. So this is 0 right here, right? So this is going to be a big V again over V minus or V plus Vs. So if it's coming towards me, what would it be? It'd be V over V minus Vs, right? So it would be how I'd calculate the frequency as it's coming towards me, right? Problem is I don't know any of those velocities, and I don't even know the original frequency. So it's like, what do we do? Well, we just shut down. No, we don't. We keep going. So if I take that would be the frequency that it's coming towards me. What about the frequency if it's going away from me? Well, that would be F times V over V plus Vs. So I can't figure that out either, right? But what do know? I do know that this frequency as it's coming towards me, this one here, should be twice as much as when it's going away from me right here, right? Because this note here is 1 octave above whatever this note is going to be right here. So what I'm going to do is I'm going to take this entire equation up here and divide it by this entire equation right here. Okay, I'm going to take that whole equation, divide it by that, and that should equal what? It should equal 2, right? Because this frequency up here, this whole frequency up here is 1 octave above this frequency here. It's twice as much as what this one is. So if I divide this equation by this equation, it should equal 2. I think that should make sense. I hope that makes sense. Okay? All right. These frequencies here will cancel out, see? See, we didn't need them. We didn't actually need to know what the actual frequency of the object is. Now, how do I take this fraction divided by this fraction? Well, I'm going to flip this fraction and multiply by the reciprocal, right? So I would do V over V minus Vs, and I would take that times V plus Vs over V, and that should equal 2. And of course, those will cancel out. And I would get V plus Vs over V minus Vs equals 2. I can multiply this bottom part up here by the 2, and I would get a V plus Vs equals 2V minus 2Vs, right? And then I could combine the Vs's. I could take this V over this side, and I could take this minus 2Vs over here, and I would get, I get 2V minus V would be a V over here, and then I'd add this 2Vs over here, and I'd get a 3Vs, right? Okay, and the question is, how fast is the object moving, right? That's Vs. What is Vs? How fast is the sound source moving? So Vs would equal the speed of sound divided by 3. Check that out. Speed of sound divided by 3. What was the speed of sound? It was 330. So 330 divided by 3 equals 110 meters per second is how fast this object needs to be going. I can't draw an S there for some reason. Okay, too close to the end of the iPad. Okay, so this is, we don't ever need the frequency. You don't even need to know how fast anything is going. If you have an object, we don't even know what the temperature, we don't even care what the temperature is. If you hear an octave drop in frequency, if like a race car goes by and you hear a total drop in frequency, that means that object is going 1/3 the speed of sound. Whatever the speed of sound is on that day, on that temperature day, the object would be going by you at 1/3 of that speed if you actually heard an octave drop. I thought that was kind of a cool problem. I don't know if you did or not, or if you're getting really bored with all this quarantine stuff. So we're going to QED that. You should be able to have no problem working through the eLab and taking the Jedi trial on the Doppler effect. That's going to be Jedi trial 7.3.